Hi, my name is Benedict. I've covered quite a lot of complex things in videos recently, and on my blog articles I've been talking about more of the mindset side of business. And I thought it's really been a while since I've done one of those really back to basics, far more practical things. I know a lot of people just only want to see the practical things, not the thinking stuff. I try and focus more on the thinking stuff because I know there's so little of that being put out there. But people still want the practical stuff too. So I'm going to walk you through some of that, and I'm going to take you right back to the very beginning of synthesis. And this is useful information for anybody. There are things you can learn in this that even if you're a guitarist or a classicalist or whatever ism that you put onto your thing, there are some really fundamental ideas in here that you will find that you can apply. I know that's pushing it back into thinking, but remember, I'm the thinking guy. I'm not the turn this knob guy, even though I'm going to be doing some knob turning in this. So, in this, I am going to run through the four basic wave shapes that are used to define the core of synthesis. Now, it doesn't necessarily, thank you whoever you are, it doesn't necessarily mean that this is going to rule out people who are wanting to do modern synthesis with complex waveforms. We'll look at that a little bit. But it's from those four basic forms you can make almost anything. And by understanding those basic forms, it allows you to go off and play with the weird and wonderful, scary, ugly looking shapes. So, a little bit of housekeeping. What you'll be seeing here, or what you'll be hearing, is going through a delay. Also remember, I'm using these cans, which means I am not hearing tone particularly well, especially in the low end of things. I'll often defer to the low end because you will see this display here, the spectrum display, is showing us the partials. So we've got the fundamental and then the various overtones. Each one of those spikes is just an overtone. Don't fuss too much about it. It sounds very mathy. And it kind of is, but if you get the basic idea of what that is, it's really easy, and after that it doesn't much matter. So just a tiny bit of delay, just to make it easier to listen to, because really dry sounds are, well, really dry. So let us start at the very beginning. The fundamental tone is this fella. It's called a sine wave. You'll see the shape there is very smooth. So it's just that. It's really weird doing this backwards. By being really smooth, you can actually hear that in the sound. It's a ooh sound. You know, despite bad playing, you should ironically be thinking, well, what instruments does this kind of sound like? And by instruments, I'm not meaning EDM instruments. That's fine. Use them however you want. But these are tones. But what real-world instruments sound a bit like this? Hopefully, your answers will include the flute. Because a flute, good old-fashioned orchestral flute, or even to some extent a recorder, or any of those fluty type things, simple pipe outputs what's predominantly a sine wave, a pretty clean tone. There's other bits and pieces, your breath and little distortions, but that's the fundamental of what you're hearing. So a flute is a pretty good example of an instrument that's close to a sine wave in its output. The other thing that hopefully you may have picked is an organ. And an electronic organ, rock organ, what have you, often you're hearing lots of overtones, lots of partials being played, but its core sound is just that. And everything else that you hear is made up of other things, which you'll start to understand as we go forward. It's a basic tone. Now down here, you've probably noticed one of the things that it's super good at. Because it doesn't have a lot of overtones, that still sounds really bright. Painfully so in these things, really bright. So the first thing that we should be doing is asking ourselves the question, why is it that this sounds really deep and bassy and warm, whereas this sounds really bright and thin and not warm? Hopefully you can see the kind of Captain Obvious. There are two Captain Obviouses here. And one is the wave shape looks like this in our sine. That's what we're hearing. It looks like this. We're only hearing one partial, one tone, the fundamental. There are no overtones in that sound. Therefore, all the energy, you'll see even here that it's loud, all the energy is concentrated in the one place. Hands on screen. That means that the whole volume there is concentrated in the one tone, so wherever we're playing it, it sounds loud. And if we're playing in the bass and we have devices that are capable of reproducing that bass, it sounds meaty, it sounds grand. Up here, it's focused, but it can also sound a little piercing. But that's just because there's only one tone that we're hearing. When we swap across to this fella, playing the same low notes, we end up with that hard, harsh sound. Look at the shape. Look at the shape here. Lots and lots of overtones. Overall volume is roughly the same in the sense of the fundamental, but because we're not just hearing one tone, but we're hearing a whole lot of things at once, like a whole lot of people talking at once, listening to one person in the room is very focused. Put 100 people in the same room, thank you, then suddenly it's loud. That's because you've got lots more going on. So these are the real fundamentals, and understanding them makes a big difference. Smooth look and wave, smooth sound. Wave with a hard curve in it, as it gets to the bottom and then starts again. See here? Shark tooth shape. That creates a hard sound, which is all those overtones. So if you're looking for a warmer sound, you want to get rid of some of these overtones, which brings us to the number 2 part of synthesis, and that's adding filters. No filter, add a filter that's doing nothing, close to the same sound. Not exactly, but close enough. So for the moment we'll say exactly the same sound because it's doing nothing. We roll that off. So we're warming the sound by actually removing the number of overtones. Hear how that gets back to being quite similar to the sine wave. Not quite as focused, but we do have a bit more going on. Take the time to really understand that, so that if you've only got a pure tone, so if I'm playing C1, you're only hearing a tone which is C1. Doesn't matter what tuning method you use, it's still C1, you're only hearing the one tone. If I play C4, you're only hearing C4, which we can't because I filtered it out. So the filter is merely changing the volume of the upper harmonics of a sound. It's a tone control. It's all it is. It's just more dramatic than the one bass and treble on your stereo, which are 6 or 12 dB. This is 24 dB per octave, so it's just turning down the volume. Everything there. But we're not going to get too much into filters. But at core, and this is the real thinking bit, now, everything you do, whether you're an EDM guy, a classical guy, a rock guy, a Jamaican dancehall guy, everything is tone or timbre, which is kind of a fancy French word for tone. So, kind of warm. Yummy. Subby. Harsh. What we have coming out as a wave shape is merely changing. And the change is between a sine and, in this case, a sawtooth. If we pop over to our buddy here, we can move between a triangle and a saw, or a saw to a triangle to a saw. I'm on 50%. There we go, perfect triangle. We'll come back to that in a moment. So let's go back to Thor. Here's our triangle. There's our sine wave, no overtones. Well, maybe one or two, because the world is never perfect, and if it was, it sounds dull. We have overtones. Not enough to be super bright, but we have overtones. But the wave, if we look at the wave shape, it's still fairly smooth. It's a wee bit pointy there and there, which is here, here and here. But overall, it's still closer to this than it is to that. Let's listen. Swap engines. See how that brightens up more dramatically the more we make that angle there sharp. So this is one of the fundamental things about tone. The more we make the movement of that waveform sharp, the sharper the sound. The sharper the sound, the more overtones we have. So it doesn't matter how you think about creating the process. If we were to say, start with, actually we'll do it over here, it's going to be easier. If we were to start with C, that's the way. If we were to start with C, play an octave above, we've given it an overtone, 2 octaves above. That's just me having to do the hard work of playing my tone and an overtone. If I was really fancy, I could then use velocity to control it. Wasn't too hard. But essentially that is what an electronic organ is doing. Your Hammond B3, any of those sorts of things are just allowing you to control the overtones, what's called an additive synthesizer. But it doesn't matter whether you're creating a wave shape here that looks like this, in this kind of a format, see this sort of format, or in this sort of format. If I was to say I'm going to draw in partials here, 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 and here, we'd get a new wave shape that was drawn this way. If we were to create a wave shape here they would be represented in the fundamental and number of partials here. So it doesn't matter which way you get in your head first. Personally, I find this easier to get, but some people find this easier to get. Whichever you get is absolutely fine. But fundamental core idea is that the sharper looking this shape is, the more activity you have up here, but more importantly, because we don't care about graphs, I considered doing this without this on at all, but I know it's going to help some of you. The smoother the shape, the smoother the sound. The pointier the shape, the pointier the sound. Very, very simple to understand. Sure, we've got pitch. And there's a feeling that a sound becomes pointier as you go higher. A tiny violin sounds pointier than a big-ass violin. Or it could be a cello or a double bass, but it's essentially the same thing. They're all kind of violins. I know some classical people would want to hit me with something, but really, look at the damn things. They're all just fiddles. There's little fiddles, mid-sized fiddles, big-ass fiddles. The tone difference is based partially on the size of your fiddle, the length of this fiddle string, which creates pitch, and the rest of it's timbre. Fiddles roughly sound like one another, whether you're going from the littlest ones to the biggest ones. There's not a massive amount of difference. I know some people can be, but it's like the difference between playing a Fender guitar and a Gibson guitar is that you can get all anal about it and fine on your own time, but an electric guitar really sounds like an electric guitar. And unless you are being anal about it, an electric guitar is an electric guitar, and you really couldn't give two hoots when you're listening to Kiss or REO Speedwagon or Pearl Jam or whatever brand of gear they're using. You don't care. What you're listening to is pitch and timbre, or tone. So, if you want a warmer sound, you're looking for a smoother waveform. If you're looking for a brighter sound, you're looking for a pointier waveform. Here's another way that we can look at how we define pointiness of waveform, because we're going to roll in another little bit of information, and this information is called symmetry. Generally somebody with a very symmetrical face, let's face my little camera here more, so a face that if you cut it in half, this half looks like this half. So if you folded them together, they'd be the same. People with more symmetrical faces we generally think are better looking. People with wonky faces we generally think are less good looking. Pure biology. Same happens with waveforms. When this waveform is this shape, remember, it's smooth, warm sounding. Sounds nice. When it's not symmetrical, or asymmetrical, as in it's all off to one side, it's a bit harsh, it's a bit rough. Ugly. Which is why we use filters to essentially turn this harsh sound back into this sound. Go figure. That's why you can actually use an additive synth, something that has no Moog style filters, and still make beautiful sounds. You've just got to understand how to control tone. And having that sense of how to control tone means that you can start to change the tone without buying a new instrument. And again, this goes across the board from whether it's EDM to metal guitarists to fiddle players in orchestras. you can change your tone. And that changes the feel, changes everything. So what we're going to look at here, and really look at symmetry, is this fella. That is one ugly ass sound. Look at that wave shape. 90-degree turns. Not fun. Do that in your car at high speed and see how it goes. Not fun. End up upside down in the weeds. This is a hard thing for things to do. So forcing them to do it means that you're going to get a hard sound. Not a wrong sound, but a hard sound. Think of it this way, and if you've got nice speakers, think carefully, what's that speaker actually doing? When we've got our triangle wave, which looks like a triangle, your speaker is going like this. When we're asking it to output a square wave, your poor speaker cone is having to go How well can it do that? In reality, not very well at all. Is that a problem? Actually, no. Because the problems that it has with doing that are the things that we love in music. Subject for another article or argument. There's stuff here in my book about it. But more complex waveform, it's harsher. You get a harsher sound. Still plenty of fundamental. Lots of stuff happening up here. Not going to get into discussing the nature of the overtones and their relationship to one another. Who really cares? You can get into it in the math and it's interesting, but you don't need to know. You just notice that that has one kind of sound. It's got one relatively harsh angle. This has got two harsh angles, and it's a kind of a sound. It's harder, but we can make it harder still. Now notice what's happening up here. Look at the nature of this shape. As we do this, what we're actually looking at is this. With a pulse wave, with a good pulse wave generator, when you get all the way through, you've essentially got nothing. You're opening and closing that up down so fast that nothing's happening, so the sound turns off. Disappears up its own mathematical backside. When we're really tight, as we get tighter, notice how normally the sound loud here, quiet there. Loud here on the fundamental gradually gets quieter as it goes to higher overtones. As we tighten this pulse up, notice how this is dropping. In other words, it's lowering in volume or intensity, meaning that the relative volume or intensity of the overtones gets higher. What you're hearing is something that's more and more unpleasant. It's harsher and harsher. Why? Because we've gone from beautiful symmetrical me to very unsymmetrical, which is exactly the reaction we have to that sound. Doesn't mean it's a bad sound, doesn't mean it's a useless sound. It's actually a very useful sound. But just get you having in mind the idea that these shapes that you see actually represent, to some extent, what your speaker cone is doing. I'm speaking broadly here, so if you're an audiophile, don't send me hand grenades. Understand the value of what I'm trying to get across. Is that it could be moving nice and evenly, or it could be moving, slows down, and then comes round and slows down, which is very soft and gentle on the speaker cone. It can be moving perfectly like that, which is not too bad on the speaker cone. That sudden movement from there to there, which is your top of your peak or your bottom of your peaks, troughs, there's a little bit of an issue with the speaker at that point. It doesn't want to change direction. None of us ever want to change direction. There's some physics law about that. We hate changing directions at bottom line. This fella, it's going along nicely, and then suddenly it's asked to go back and do it all over again. So at that sudden point, it has some distortion, so that creates that harder, more bright overtones. But not too much. Then when we have here, we've got that poor speaker having to move and wait, and then move and wait, and move and wait, and oh, nasty. Nasty indeed. So we end up with a really, really bright tone, and as a result of that, it can't actually develop its bassiness, its bottom end, its fundamental, because it's moving too fast for that. In a sense, it's becoming more distortion. You see this wave here, looks pretty messed up. Some of that has got to do with Nyquist frequencies and how samples are handled and stuff. Again, I don't care. And I don't think that you should care either. If you're looking to be some kind of scientist, brilliant, care a lot. But if you're just looking to get the tone that you're looking for, more importantly to get the story or the feel that you're looking for in your piece, don't give two shits. Ignore anybody who tries to tell you that that stuff's important and a fundamental. It's not at all. The fundamentals are the pitch, the tone, if I swap that across to here, two different tones, completely different tones from different shapes. If we were to use this fella, very similar, except I had a 12 dB. So it actually doesn't really matter how you create a sound. I know that's going to freak a lot of you out, because a lot of you are going to go, oh, you need this instrument to make that sound. No, you merely need to know how to make that sound. A lot of us are lazy, and that is okay, so long as you understand that you are being lazy. You've got a perfect right to do that. You don't want a car that drives faster, rather than learning to drive faster, you could just buy a car with a bigger engine. That's okay. If you've got the resources to A, go buy a whole other car, and a more expensive one because it's got a bigger engine, and B, put all the petrol in that sucker so you can drive faster, brilliant, go for it. If, however, you're looking for economy, stay with the car you've got, learn to drive it better. I used to be in the car game. I actually specialised in a little tiny car that drove incredibly fast. And one of the problems that I would have is kids would come in and go, oh, but does your car drive as fast as that twin-turbo Supra? And of course it fucking doesn't. But I wasn't quite as blunt back then. So I'd say, okay, well, how does that twin-turbo Supra go up against a Porsche? Oh. You want Porsche speed? Go buy a Porsche. Where the cost? Where the insurance? But in reality, on the road, you can only go 60 kilometres an hour in Australia, or 100 kilometres an hour out on the freeway, 110 if you're lucky enough to live near one of those zones. I mostly drove around in a 1.5 litre car, single overhead cam, naturally aspirated. It's a basic little sucker. But I could actually take 6-cylinder cars at the lights with it, because I knew how to drive the damn thing. I wasn't the world's best driver, but I could just watch the lights count, and instead of waiting for my car to do it for me, which they were doing behind me, I'd be gone. I'd get to 60 before them. Once their engine got itself spooled up, I was toast, but who cares? any idiot can go fast. The finesse is in learning to use your tools. So the real thinking part of this is to understand that correlation between basic wave shape and the tone that we get from that. Which leads us to then the next bit, and we'll make this the final bit about waves. We're not going to get into resonance, but we're going to get into overdrive. Let's have a good old-fashioned bit of hard clipping. Let's go back to this fella. Ooh. That's our sine wave that has no overtones. So all it can ever do is go ooh, ooh, ooh. Put in some clipping. Clipping is where your gear cannot handle that movement, that transition from here to there. It's so loud that the speaker no longer knows, or the gear no longer knows, how to make it reproduce neat and tidy. So you go outside of that box, and it goes, what am I going to do with that bit that's outside of my box? I can't deal with that. So it actually just chops it off. The way different pieces of gear chop that off, but create some of the uniqueness of their sound. But again, you don't actually need a Marshall stack to sound like a Marshall stack. You just need to have a sense of what that Marshall is doing to the tone that you are feeding it to be able to duplicate it. Don't believe me? Go out and look at one of those guitar pedally things where you just plug your guitar straight into one end of it. What comes out the other side is, depending upon whether you dial it up, a Marshall stack, a Fender Tweed, a cat crying in the Blue Note in 1967. They're very, very good. I don't care whether you like them or not. That's a personal choice. But the good ones do a surprisingly good result in that most people can't tell the damn difference. So what that tells us for sure is that tone is not a result of gear. Tone is a result of what we do. So, I've got my simple sine wave. We're going to start to clip this little fucker. Ooh! Now, do you recognize that waveform? It's somewhere in the vicinity of this. Not the same, because we've got different processes, but somewhere in the vicinity of that. So remember, we've got our wave moving nicely inside the box. We then ask our wave to move outside the box. It chops off. So your wave that starts nice and round like this actually starts to look like this. Because what would a sine wave look like if it was actually waving outside of the box? It can't just say, well, I'm no longer produce this little bit. If it did, you'd have a pulse wave of some kind, some kind of weird complex pulse chain. Because the sound still has to be created, it's not like the speaker cone can cease to exist. It's not like you can go, okay, that's as far as I can travel, I'll now cease to exist until I come back into existence. This isn't Star Trek. It still has to exist. Otherwise it would be, and that's it, you've got no speaker at all anymore, literally. Weird, freaky. Not to mention an awful lot of lawsuits. So it gets clipped or cut off, so your speaker goes out, and you're effectively asking it to stay there for the time that that wave is out here. So whilst the bit of your sine wave is out here, out beyond the box, your speaker can't go any further, which means that it can do nothing but make a nasty noise. That nasty noise, if you happen to be slash, is brilliant. If that nasty noise is because you don't know what you're doing, it's going to sound god-awful. So the nastiness of the noise is again in the ears of the beer holder, and what you're doing with it. So you can take any tone. We've started to turn that into a kind of pulse wave, you know how, because I can hear it, and getting harder, and we can see the fundamentals starting to fall away. Exactly what the wave looks like, who cares? Notice the difference in tone. I'm not suggesting that you overdrive things that much, because if you overdrive chords that much, it is ghastly. Unless your name happens to be John Lord and you're playing with Deep Purple, and then it's just unequaled. Now what we're doing here is we're shaping that, or we're distorting that after the filter. What we could do is distort it before the filter. Just a different way of playing with tone. I'm not going to get into it any further than that, merely to say that you can do it, that all you're doing is playing with tone. You are creating different wave shapes, and out of those 4 basic shapes, you can then, and to modification, you can then create a whole lot of different tones. And from those tones, you can then create a whole lot of different moods. So if you're playing really high notes in a really brittle tone, a really hard tone, a really aggressive, brutal looking wave shape, then it's going to be super bright, and depending upon how you control that, it's either going to sound very aggressive or very bell-like. But bell-like means that you've probably got still kind of a smooth tone. But if it's really harsh, it's going to be like... And EDM relies on that very heavily. So does rock. Screaming guitar solos. Really bright tone. Cuts right through. The more riff-based stuff tends to be actually quite a warm tone. There can be a lot of drive in that, but it's still quite a warm tone. So by choosing the pitch that you're playing and the tone that you're playing with, you've now got a huge amount of control over the way you're presenting your story, the feel of your story. That's perhaps a slightly different approach from what you were expecting, but I hope it's really helpful, not just to people looking at pure synthesis, but guitarists, classicalists, reggaetonists, I don't care, the concept of tone. Thank you.